The concept of linking the world's two largest continents by a physical railway beneath the sea has persisted since the time of Tsar Nicholas II. It is the ultimate conceptual challenge of global infrastructure, a project that promises to transform trade, logistics, and geopolitics by connecting the rail networks of North America and Eurasia. This massive engineering undertaking, known as the Bering Strait Tunnel or the World Link, was intended to create the planet's first continuous overland route spanning 15,000 miles from London to New York. The success of this megaproject would have fundamentally redefined global trade, making it a project that truly should have transformed the future. Before we dive into this conceptual failure, please take a moment to hit the like button and subscribe to Never Built. We uncover the lost future that the world canceled. We promise you this. Stick with us until the final segment, and you will learn the one specific, chilling geological flaw that would have guaranteed the catastrophic flooding of the tunnel, proving the permafrost was the ultimate, unyielding enemy. Here is why this ultimate engineering ambition was abandoned. The first, unanswerable problem was the permafrost time bomb. The tunnel would be constructed beneath the Bering Strait, where the seafloor is dominated by perpetual permafrost. Engineers discovered that the heat generated by the massive tunnel boring machines and the active railway would inevitably melt the surrounding frozen soil, turning the bedrock into unstable, collapsing mud. The second, inescapable hurdle was the Arctic crush. The tunnel must withstand the colossal forces of extreme Arctic conditions. The movement of multi-year sea ice and the immense pressure exerted by seismic activity in the volatile Bering Arc would constantly threaten to shear the rigid tunnel structure, leading to catastrophic collapse and flooding. Finally, the estimated construction costs soared into the hundreds of billions of dollars. But here is the critical promise from modern engineers. Even if the tunnel were built for free, the annual maintenance costs for fighting continuous geological instability and repairing equipment in the world's most inaccessible, extreme cold environment would bankrupt every nation involved. The story of the Bering Strait Tunnel is a cautionary tale that defines the limits of modern civil engineering and explains why the ultimate logistical link between East and West remains the most challenging project ever conceived. The first and most critical hurdle facing the Bering Strait Tunnel concept was not simply the water, but the geological instability and the pervasive extreme cold. The proposed tunnel route would be approximately 65 miles long, making it the longest tunnel ever constructed, far exceeding the current record holders. More critically, the route crosses the Bering Arc, a highly active seismic zone where the massive North American and Eurasian tectonic plates meet. This is a region prone to frequent and unpredictable earthquakes. Building a permanent, rigid structure across this active boundary is immensely difficult. Engineers face the certainty of tectonic shifts and seismic fault lines. Even a moderate earthquake could cause massive displacements, instantly shearing the rigid concrete and steel tunnel segments. The tunnel would need to incorporate massive, specialized seismic expansion joints to absorb this continuous geological movement, adding exponential complexity and cost. The complexity of these joints, required to flex under thousands of tons of rock and water pressure, demanded materials science that simply did not exist. The engineering trade-offs were insurmountable. The presence of permafrost compounded this geological instability. The seafloor beneath the Bering Strait is not static rock. It is largely composed of soil that has remained frozen for millennia. This permafrost acts as a rigid, stable foundation when frozen, but is highly vulnerable to thermal change. The continuous operation of the tunnel's railway and ventilation systems would generate immense heat. This heat would inevitably thaw the surrounding frozen ground, destabilizing the tunnel's foundation and turning the once rigid bedrock into an unstable, collapsing slurry of mud and water. Engineers calculated that the structural integrity of the entire tunnel would degrade over decades as the permafrost slowly melted due to the tunnel's own operational heat, making the project a guaranteed structural failure on a geological timescale. This challenge alone exposed the fatal flaw in the entire construction premise, proving that the foundation itself was built upon a geological time bomb. The catastrophic thawing process would create unpredictable cavities and pressure zones, ensuring that the TBMs themselves would struggle to maintain alignment and structural integrity during the initial boring process, a technical hurdle deemed too risky. The engineering challenge was further complicated by the need to combat the extreme Arctic environment. The Bering Strait is one of the coldest, most remote, and most inaccessible stretches of water on the planet. Construction would be limited to short summer windows, and the logistical challenge of moving massive tunnel boring machines and hundreds of thousands of tons of materials across Siberia and Alaska was immense. Furthermore, the completed tunnel would be subject to massive ice scour and ice pressure from the movement of multi-year sea ice in a shallow strait. While the tunnel would be buried deep beneath the seafloor, the surface infrastructure and access points will be constantly threatened by these powerful ice forces, requiring massive, costly, and heavily reinforced protective structures on land and in the nearshore environments. This extreme inaccessibility meant that any operational failure or maintenance requirement will be exponentially more difficult and expensive to resolve than in temperate regions. The severe wind chill and perpetual darkness of a long Arctic winter would make emergency repairs virtually impossible for 9 months of the year, adding another layer of unmanageable risk to the operational budget. The tunnel's proposed construction method demanded the largest and most robust tunnel boring machines, TBMs, ever built. These TBMs would have to be nuclear-powered or supplied by immense surface energy stations, given the extreme length and the requirement to operate continuously in remote Arctic conditions. Furthermore, the TBMs would have to be capable of tunneling through a highly unpredictable mix of hard rock, soft sediment, and unstable permafrost. The sheer size and cost of the TBM fleet needed for this decade-long project were prohibitive. The environmental liability of operating nuclear TBMs or managing massive, centralized power plants in a pristine Arctic environment also raised immediate political and environmental red flags. The cost of a single, stalled TBM deep beneath the strait, too large and too contaminated to retrieve, would result in a massive financial write-off. The necessary investment in specialized, super-heavy TBMs added billions to the overall budget, proving that the most advanced technology was still defeated by the raw, brutal environment. The sheer logistics of supplying and maintaining a drilling operation of this scale in the remote Arctic meant that every minute of downtime would equate to tens of millions in lost investment. The final logistical failure lay in maintenance and safety. Assuming the tunnel could be successfully bored, the long-term maintenance of the structure and its rail line would be an unprecedented nightmare. The cold, humidity, and constant seismic stress would relentlessly attack the concrete and steel. Repairing a structural crack or replacing a worn rail section would require highly specialized teams operating in the crushing cold and isolation of the Arctic deep. Any failure of the ventilation or drainage systems within the tunnel would quickly lead to flooding or the buildup of poisonous gases. The remote location meant that rescue and maintenance teams would face days of travel in extreme weather just to reach the operational area. The entire system lacked the necessary logistical redundancy for a safe public and commercial transport link. The project was strategically unsound because the cost of a single major failure and the subsequent years of repair would be so immense that no global consortium could bear the risk. The second phase of the Bering Strait Tunnel failure involved the political and economic instability inherent in a project that spanned 2 continents with vastly different strategic interests. While engineers focused on the rock and ice, financiers faced the reality of a massive investment vulnerable to geopolitical shifts. The estimated cost for the tunnel itself consistently exceeded $100 billion, but the true fiscal catastrophe lay in the necessary ancillary infrastructure. Connecting the tunnel to existing national rail grids was a challenge of comparable scale and cost. The Siberian side required building thousands of miles of new, heavy-duty railway across undeveloped, permafrost-ridden wilderness. This necessary link, the Trans-Siberian Extension, was a mega-project in its own right, projected to cost an additional $60 to $80 billion. Similarly, the Alaskan side required upgrading and extending the rail lines to allow heavy freight traffic to cross the vast North American continent. The combined cost of the ancillary rail infrastructure alone often doubled the total financial outlay for the entire concept, making the World Link not a $100 billion tunnel, but a $250 billion continental infrastructure network, a figure that no single nation, nor a stable consortium, could realistically absorb or guarantee. The financing model for such a colossal project was entirely unprecedented and ultimately unworkable. Typical large-scale infrastructure projects, such as the Channel Tunnel or massive bridge systems, are financed through a combination of public funds, sovereign guarantees, and private equity, with expected returns generated by tolls and tariffs. The Bering Strait Tunnel, due to its scale and extreme location, could not rely on standard metrics. The revenue generated from freight passing through the tunnel, while significant, would take centuries to repay the principal investment and cover the astronomical maintenance costs. The inherent political risks, including sudden changes in tariffs, border closures, or international sanctions, made private investment nearly impossible to secure without 100% sovereign guarantee from every nation involved. The project lacked the financial stability required for private capital, and it was too expensive for public treasuries to fund alone. This financial chasm was an economic law of physics that ultimately proved stronger than any TBM. The issue of strategic vulnerability haunted the project, mirroring the concerns that plagued the transatlantic tunnel. A single, fixed infrastructure asset connecting two geopolitical rivals represented a critical single point of failure. In times of heightened tension or conflict, the tunnel would become the primary strategic target. Disabling the tunnel, either through conventional sabotage or military strike, would instantly sever the global trade link, causing economic chaos. Both the United States and Russia would require massive, permanent military installations and security protocols at both ends, and complex, submersible security systems along the entire route. The cost of guaranteeing the tunnel security against hostile state actors or terrorist threats was never fully factored into the initial feasibility studies, but it would have added tens of billions to the operational budget. This military burden transformed the project from a civilian logistics route into a strategically critical, high-risk asset that demanded perpetual military protection, making a liability rather than a purely economic benefit. The permafrost melting problem was studied in depth and revealed a chilling geological reality. The soil beneath the Bering Strait is filled with pockets of frozen methane and ancient water reserves. As the heat from the tunnel operations radiated outwards, the permafrost would not just turn to mud. It would release trapped gases and create massive, unpredictable subsurface cavities. These cavities would lead to differential settling, where one section of the tunnel would sink relative to another. This differential settling would put intolerable shear stress on the tunnel segments, well beyond the capability of even the most advanced seismic joints. Furthermore, the thawing of frozen water pockets would introduce highly pressurized water flows into the tunnel environment. These high-pressure water inflows would overwhelm the internal pumping and drainage systems, leading to localized flooding and accelerating corrosion. The engineers faced a scenario where the tunnel was not simply passing through rock, but through a dynamic, chemically and thermally unstable geological medium that was guaranteed to change and degrade the structure over time, a technical failure with no long-term solution. Another crucial engineering failure related to ventilation and temperature control. Due to the extreme length of 65 miles, the Bering Strait Tunnel would require monumental, continuous ventilation to provide fresh air, remove exhaust fumes from diesel locomotives used for backup power, and, critically, manage the internal temperature. To prevent the permafrost from melting, the temperature inside the tunnel needed to be maintained as cold as possible. This demanded a constant, massive energy expenditure for chilling the air and the structure itself, especially given the heat generated by the moving trains. Cooling a 65-mile-long tunnel is an engineering feat that requires power plants comparable to those needed for small cities. Conversely, the air entering the tunnel from the surface in the Arctic winter would be lethally cold, potentially freezing equipment and rail lines. Engineers were trapped between two opposing necessities: cooling the ground to prevent collapse versus heating the interior to maintain operational viability. This thermal management paradox contributed significantly to the project's prohibitive long-term cost and its ultimate abandonment. The energy expenditure for this perpetual thermal battle became the final insurmountable operational expense. The third and final phase of the Bering Strait Tunnel's failure was dictated by geopolitics, liability, and a sheer impossibility of cost recovery. Even if the engineering obstacles of permafrost and seismic activity were overcome, the project was financially and strategically unsound for the long term. The projected price tag for the tunnel alone was consistently estimated at over $100 billion, a number that ballooned when factoring in the necessary infrastructure and the astronomical maintenance costs. Building the tunnel was an engineering marvel, but maintaining it in the face of continuous tectonic stress and extreme Arctic conditions was an economic law of physics. The required perpetual effort to combat ice pressure, material fatigue, and seismic instability would consume billions annually, proving that the project was too expensive for sustainable commercial viability. The political volatility of the project was an insurmountable hurdle. The tunnel connects the territory of the United States and Russia, two nations with historically tense and unpredictable relations. While the tunnel promised global trade benefits, the security risks associated with a fixed, underground link between geopolitical rivals were enormous. The tunnel would represent a critical single point of failure in the global trade route. Any military conflict, even a localized border dispute, or the imposition of sudden political sanctions could instantly close the link, paralyzing global commerce and nullifying the multi-billion-dollar investment. Neither government was willing to entrust its primary continental trade access to the political whims of the other. The immense cost and strategic importance meant that the tunnel would inevitably be viewed as a military liability and a prime target for sabotage or attack in times of conflict. This necessary geopolitical stability, spanning centuries, was an assumption the project could never reliably guarantee. The problem of liability and disaster response was similarly crippling. The Bering Strait is shallow, but the extreme cold and remote location make any deep-sea recovery or repair operation impossibly difficult. A catastrophic failure or flooding of the tunnel would result in the loss of hundreds of lives and require a repair effort of unprecedented scale, conducted in continuous darkness and lethal temperatures. The insurance industry and international financial bodies refused to underwrite the risk for a project of this magnitude in such a hostile, remote environment. The concept of limited liability was fundamentally incompatible with a tunnel that required absolute perfection over 65 miles of volatile subsea terrain. The required safety protocols and the cost of maintaining a dedicated, permanent emergency response force capable of operating in the Arctic deep were another insurmountable addition to the operational budget, confirming the project's financial absurdity. The project was also undermined by the absence of necessary infrastructure and supporting logistics. While the tunnel itself was the centerpiece, its commercial viability depended entirely on the existence of continuous, high-capacity rail links on both sides. The Siberian rail link required building thousands of miles of new track through completely undeveloped permafrost, a massive undertaking prone to delays and structural failure due to thawing ground. The cost of this necessary extension alone rivaled the cost of the tunnel. Similarly, the Alaskan rail link required extensive upgrading and expansion across the state's undeveloped interior. The logistics of supplying the construction sites, maintaining the remote rail lines in the Arctic climate, and ensuring security across thousands of miles of wilderness added layers of operational and economic burden that were simply ignored in the initial optimistic projections. The World Link was a logistical fiction, relying on the assumption that two massive, expensive, and politically challenging rail extensions would materialize simply because the tunnel was built. The environmental impact of the Bering Strait Tunnel was another powerful factor in its cancellation. The Bering Strait is a narrow, ecologically sensitive gateway that connects the Pacific and Arctic Oceans, influencing global currents and supporting unique populations of marine life. The construction process, involving massive dredging and tunneling, would inevitably disturb the seabed, threatening vulnerable ecosystems. More importantly, the continuous operation of the tunnel, with its thermal output and the potential for a catastrophic flood or leakage, posed an existential threat to the delicate Arctic marine environment. The release of warm water or industrial contaminants into the cold, shallow strait could alter local climate patterns and severely damage marine habitats. This environmental risk, combined with the extreme political difficulty of gaining regulatory approval from two hostile nations for a project in a globally sensitive area, provided another definitive reason to abandon the project. The ultimate fate of the Bering Strait Tunnel project lies in the triumph of economic and geological reality over utopian ambition. It was not a technological failure, as engineers were confident they could design TBMs capable of boring through the rock. It was a failure of scale, stability, and finance. The project demanded an investment that would take centuries to repay, required perpetual maintenance in the most hostile environment on Earth, and was constantly threatened by the natural forces of tectonic movement and permafrost thawing. The economic case simply collapsed under the weight of the necessary security costs, maintenance liabilities, and external infrastructure requirements. The dream of the World Link remains the ultimate unfinished megaproject, a powerful reminder of the physical and financial limits of human infrastructure. The final crucial analysis that destroyed this dream was the discovery of unstable, ice-rich permafrost layers directly beneath the proposed route. Engineers calculated that the heat from the tunnel would not just melt the ground slowly, it would create massive, unpredictable geological voids that the structure could not span. This would have guaranteed the collapse of the tunnel before the first train ever ran, proving the Arctic always wins. The final question remains: given the current advancements in automation, high-strength carbon fiber composites, and autonomous TBMs, do you believe that a future generation will ever possess the technology and the political will to connect the continents beneath the abyss? Or has the combination of permafrost and tectonic activity definitively won this engineering war forever? Let us know your thoughts on the future of transoceanic travel and tele-US. Which country would be most responsible for the cleanup if a segment of this trillion-dollar tunnel collapsed? If you enjoyed this professional deep dive into the abandoned engineering of the Bering Strait Tunnel, like this video and subscribe to the channel for more stories about the incredible projects that were never built.